This is question 9 out of the homework. Gurkir, does that kind of make sense? It's the going there and back. I think that was probably messing you up. Because not to expose anyone, but that was the same question Connor had at the end of the day yesterday. Number 10, you said as well, a woman from Pasadena makes a trip to a nearby shopping mall that is located 40 kilometers from her home. On the trip to the mall, she averages 80 kilometers per hour, but gets a speeding ticket upon her arrival. On the return trip, she averages just 40 kilometers per hour. What is her average speed for the entire trip? That's a good question. Let's look at this. So we want average velocity, and that is, it specifies, we want average speed. That's different. Because average velocity would be, be 0. Because for the entire trip, she starts and ends at the same spot. So the wording of the question, the language is important. It asks for speed, which means we need total distance traveled over total time taken. So speed, not velocity. Velocity would be 0. So this here is total distance. This is total time. And again, this is going to be another one of those questions that's going to be helpful for us to draw out. So your drawings can be as involved or as not as you want. Sometimes, it's fun to, you draw a little car, a little box. She's driving a van. She's in Pasadena. They drive vans in Pasadena. She's going to the mall. This distance here, we're told is 40 kilometers. So what's the total distance going to be for her trip? 80. So average speed is going to be 80 kilometers. Now we need time. Time is the interesting thing, because her total trip is made up of 2 pieces, one going that way and one going this way. On the way out, she was going, her speed was 80 kilometers per hour. On the way back, it was 40 kilometers per hour. Both trips, the distance was 40. So we now need time for each piece to figure out what our total time is. So this one's actually, because the numbers are so nice, this one's actually really easy to do. That's our speed. What is time for the way back? 1 hour. 40 kilometers at 40 kilometers per hour. So that time is going to be 1 hour. And for the time going to the mall, she's going 80 kilometers per hour, which is interesting because Pasadena's in California, so this should be in miles. But whatever. She's going 80 kilometers per hour for over a 40-kilometer distance. So how long is that going to take her? Half hour. Sorry? 30 minutes, yes. But do we want 30 minutes? No, because we've got kilometers per hour here, and so we want to make sure our units are consistent. So yes, while 30 minutes is correct, I want to write it as a decimal of an hour. So our total distance is 80 kilometers per hour. Our total time now is? I'm pretty sure Connor did this in his head. T equals D over V. So 40 kilometers divided by 80 kilometers per hour. 40 divided by, that's a half. And then 40 divided by 40 is 1. And the time's going to be in hours. So the total distance is 80. The total time is? Total time? 1.5. Because time adds. So we've got 80 kilometers in 1.5 hours. 80 divided by 1.5. What's 80 divided by 1.5? 53.3 repeating kilometers per hour, which, lo and behold, is a totally acceptable answer. Yes, sir?
I did it a different way.
How'd you do it?
I got the times as well, but I averaged averaged the two times. So, because I knew 0.75 was the halfway marker between a half and a full hour. So, I just did that over 40, or sorry, under 40, which also got me 53.2.
The math checks out, but why you would do that, I don't know.
I don't know either.
So you average the time for each trip? Yeah, that works. Yeah, that works. Not how I would approach it. But yeah, no, that works. Agri-Kira, does that make sense how I'm thinking through this? Okay. Any other questions from the homework? There was 12, actually there's 14 questions. The first two I gave you answers for specifically, and then the other 12 I didn't give you the answers for specifically. I just had them on the bottom. We're good with all of that? No comments, questions, concerns? Yeah, Jasmine.
Can you explain 11 and 12?
11 and 12. A cross-country race car driver sets out a 100-kilometer race at the halfway marker. Her pit crew radios that she averaged only 80 kilometers per hour. How fast must she drive over the remaining distance in order to average 100 for the entire race? So, here's the entirety of the race. 11 is very similar to 10. You want average speed. You want the average speed to be 100 kilometers per hour. This distance is 50 kilometers. This distance is 50 kilometers. We know that she was going 80 kilometers per hour here. This is the speed we don't know. Is there anything else we need? I don't think so. So we also know that the average speed is equal to the total distance over the total time. So how do we want to go about doing this? I'm not totally sure, so I'm just going to start finding stuff. The time for this chunk, T is going to be D over V. So it's going to be 50 over 80. 50, is that 0.625? 50 over 80? 0.625, that's hours. We don't know this length of time. It's not super useful to us. We know we want this to be 100. Interesting. Yeah, we thought, Connor. What'd you do?
Well, yeah, because if you wanted to go 100, then you just go 50 over 100 to get that time. So we know what it would be to be 100.
For the total time.
Yeah, and then you
I like it.
that from the time you had at 80.
Smart man here.
And you just have
So we want 100. Yeah, so let's explain what Connor's talking about for everybody and the video, because Connor's absolutely right. We want 100 kilometers per hour, and we know the total distance is 100 kilometers. So we want this time to take 1 hour. So if the entire trip takes an hour, and she's already been going for 0.625 hours, how much time remains?
3.75.
It's going to be 1 minus 0.625, which is going to be 0.375 hours. And so the velocity, I like this, that's smart, man. So with the velocity we want then is going to be, or the speed rather we want then is going to be 50 kilometers divided by 0.375 hours, giving us a total speed of, what's 50 divided by 0.375? That's 133 kilometers per hour. I like it. Well done, Connor. Jasmine, that makes sense? I like it. And you wanted number 11 too. Cross-country, no, that was 11. 12, a supersonic jet travels around the Earth at an average speed of blah. Its orbital radius is blah. How many hours does the trip take? Ooh, good question. Why is orbital radius nice to have here, Connor?
Yeah,
because the plane is traveling around the Earth, and so the distance it travels is going to be a circle. And so we need the circumference of that, like the circumference is the distance around that circle. So by giving us the orbital radius, we can use the radius to find circumference. The formula for circumference is 2 pi r. That was number 11. So now let's actually go around and do this. So we've got a plane. There's my Earth. Here's, I'm over-exaggerating here. This is the path the plane is taking around the Earth. There's my plane. We know that the velocity of the plane is, or the average speed it gives us is 1.6 times 10 to the 3 kilometers per hour. Things trucking pretty good. We know that the radius of its flight path is 6.5 times 10 to the 3 kilometers per hour. So it's a couple hundred kilometers above the surface of the Earth, if I'm not mistaken. If I remember my numbers right. But that's the radius. That's not the distance from the surface of the Earth. That's from orbital radius is measured from the center of the circle. So that's the center of the Earth. It would be the middle of that circle. So the distance here is just going to be the circumference of the circle. So that's just going to be 2 pi r. So it's going to be 2 times pi times 6.5 times 10 to the 3. So then the time, how many hours does this take? Because this is given to us in kilometers, I think. Yeah, it's given to us in kilometers, and this is kilometers per hour. We can just use this exactly as it's written. T equals d over v. So that's going to be 2 pi times 6.5 times 10 cubed over 1.6 times 10 cubed. The nice thing here is those 10 cubes are going to cancel. So if you actually shove it in before you start calculating numbers, it is actually going to end up looking a little bit nicer. So our total time then is going to just be 13 pi over 1.6, whatever that is. Because 2 times 6.5 is 13, and my 10 to the 3s have canceled. So 13 pi over 1.6, that's 13 times 3 is 39 divided by 1.6. What's that going to be? It's going to be that 26 hours, I think. Okay, well, yeah, and so we're going to be around that 26. The answer key rounds it to 26. So the answer keys, if you haven't figured it out, don't give you necessarily exactly what you get. They take into account the fact that you guys could round as you're doing it and get a bunch of different values. Effectively, what you're looking for is an answer that rounds to one of the ones down there on the answer key. That will give you what you're looking for. So that's 9, 10, 11, 12. Any other comments, questions, concerns about any of those? Cool, we're happy with this. It's relatively easy. Kind of, sort of. Fantastic. Close your book. Grab something to write with. You'll need a calculator. You don't need a formula sheet because the formula sheet's on the, or the formula, the only formula you need is on the wall. Close all your things, put it all away. Writing utensil, calculator, that's all you need. Because V equals D over T. It's on the board. Let's see how the homework went for you guys. We're going to find out. It is an assessment of your understanding as it sits right now. Explain over. You had me as a teacher, and you haven't. So I'll explain how things go. No pressure. Don't know what you can do. That's Angela. Cool. All that will prevent you from writing this thing. I'm happy to lend you a calculator. Absolutely. So if you could pass that down to Kristen when you got that. Bam, bam. Name on this thing. Oh, yeah. I did it again. I didn't leave you a space for the name on the top. You can put the name on the top. Thank you. One side. No. There we go. on here? Give me 10 minutes to do it. See how it goes. 2.5 minutes a question. Any more to give her? I really should just have these in a box. Something of value, take a calculator. There it is. There it is. Okay, Angela.
Yeah. No, that later. That's it. Oh my god, that would have been terrible. That would have been terrible. I'll go back to the question of the is it, or this is if you go into the room for that one right now? Okay. Maybe you're able to do it without looking at what you've done. Okay. Yeah, here's that one. So now what they're doing, one of those is really done. Yeah, now, get a question from them. Get a person and stuff that he did and put it on there. So we did that kind of that was that year. I'll get back to that one. Yeah.
So here we go. Right, I was also going to explain the hole punch situation. So I don't know how it happened, but our photocopier got repaired not that long ago. And in the process of fixing the copier, the guy responsible for fixing the copier actually damaged a different part of the copier. The part that aligns where the holes get punched. So this line, oh, that's sad. I don't see it. Oh, it's there. Come here, you. Come here, you. There we go. So the part of, this is just a great morning. These holes right here are the ones that the photocopier threw in. That one, and that one. And then I realized that sucked. And then went and added these 3 vertical ones. So hopefully those fit in your binder nicely. So that's the hole punch situation. The next couple booklets I also photocopied this morning, and so some of them are going to be a little offset. I didn't realize it was screwing the holes up until like 3 or 4 copies in. So the rest will only have one set, the set that I made myself. So here we go. You've already kind of done this for me, but we're going to look at it in a little bit more detail. This is going to be a lesson on distance / displacement versus time graphs. And in fact, actually on the beginning here, I'll toss position in here as well. Position versus distance, position, distance, displacement versus time graphs. They all are very similar. The relationship between position and displacement is what, again, if we remember? What is the relationship between position and displacement? What is the definition I gave you for displacement? Okay. How does that relate? What is position? Where you are right now. So your displacement is a look at where you are now versus where you started from. Yes? Displacement is just a change in position. So when we graph a position versus time graph or a displacement versus time graph, we are effectively graphing the same thing here. So anyway, let's do it. We've got a graph here. We've got a position measured in meters north. So there's a lot of information here. What that means is as you go positively, these numbers here represent meters, and they give us the direction, so we're going north here. As we go down this way, what does that tell us? South. Okay, cool. What's happening here in the graph on section A? Talk to me about what's going on there. Yeah.
As time increases, you're moving more now. Slope north.
Okay, so I'll say it the way Connor did. As time increases, we move north. Okay, cool. Can anyone be more specific? Connor wants to be more specific.
As time increases to 3 seconds, you have moved approximately 30 meters north. That's meters seconds.
Okay, so after 3 seconds, we've gone 30 meters. Okay, what can we do with that? We could find the slope. Slope is equal to rise over the run. This is just like the graph you did, at least this part, or the lab you did, just at least this part of the graph. Rise is 30 meters. The run is 3 seconds, and that's actually 30 meters north. So then what's the slope? Manuel's out of hand? Stop drawing on the back of Connor's head. Manuel, finish it up. What's the slope?
What do we got? That is going to be 10
10 what?
meters per second.
So on a position time graph, or a displacement time graph, or a distance time graph, what can we find? What have you just done? What does this represent? On a distance time graph, this would represent speed. On a position or displacement time graph, this represents velocity. That's fun. Which you've already kind of done before. What else can you tell me about this graph? A is going, let's stop zooming in just on A. Let's look at the bigger picture here. What else can you tell me about this graph? Someone other than Manuel. Yes, hands up. From 3 seconds to 6 seconds, we're not moving. How do you know? How do you know you're not moving? Because this. How do you know? Okay, so if we just go look here, we can read off this entire time. The line hasn't gone up, it hasn't gone down, so there's no deviating from that position here. How else what's another way to talk about not moving here? Yeah? Connor?
Say the line is flat.
Sorry?
The line is like flat.
Okay. A line that is flat has what kind of property? Oh, I thought that was a hand here. Talk to me about slope. The slope of this graph is?
0.
Slope is 0. It's flat. There is no rise. There is no, well, there's a run, but there's no rise. Slope here is 0. And we've already seen here before, slope on a graph like this represents velocity. So the slope is 0 meters per second. Means this thing's not moving. Okay, cool. Talk to me about this next chunk here. What's going on in this section of the graph? Sorry? Oh, moving south. How do you know? Because this guy, if we look at this here, it's now, we have a, instead of a rise, we have it, well, we're dropping, we're rising negatively. And we were told that the positive direction was north. So if we're going this way, that's heading south. Cool. Can you be more specific, Tristan? Just stand it up right there. Thanks, man. No, that's lying down. No, that's lying down. That's lying down. I don't want it to roll off. Stand it up on the ground, please. Connor.
You're going south 30 meters, and you're going between east and, sorry, not east, sorry, and by 2 seconds.
Okay. So what can we do with that? We could find slope again. What's the slope? The rise now is negative 30 divided by 2. So we're going to have a slope of negative 15. That's going to be meters per second. It's really tiny. I'll zoom this in a little bit. So now we know we're moving south. We know how quickly we're moving south. What happens right here?
We hit 0.
What does that mean?
You have gone beyond the starting point, or like you. The equivalent. Oh, you're in the same starting position.
Yeah. At that point there, we're back where we started. Because we started at position 0. Right here, we're back at position 0. Just reading that off the graph. And what's happening in this last chunk over here? So we're continuing to move south? Yes. Continuing south. Oh, I should that a little bit. Okay, we're continuing south. What else can you tell me about it? Connor, just keep going.
It looks like you're going south to around negative 20, somewhere around there.
Okay, it looks like it could be to negative 20. Okay.
And then at the same time, there's one more second that elapses as well. You go to negative 0.
Okay. Interesting thought. Can you give me some more concrete things about what's going on in here?
Slope is negative 20 meters per second.
Does that make sense?
No, because that would kind of mean you're going in reverse, which isn't exactly what's happening. So you could change south to a positive and north to a negative, supposedly, but that would also change the other results.
Take a look at the picture here.
Ooh.
Does the slope change at all?
No,
How do you know?
because I can see that it lines up with your ruler.
Yeah, there's no bend in the line. So what must this slope be down here in this chunk? So because the line hasn't actually bent, we know the slope has to continue on the way it has been. So the slope here is also going to be negative 15 meters per second. So this is, we're just applying what I got you guys to do in the lab that we did at the end of the last unit. Looking at what it means to take slope off a graph and reading just data off of what we're given. So, now that we've written all that down, let's go through a little more concretely here. Given a displacement time graph, we can find a few things. We can find the displacement at a given time. You've done this already. You just did it by reading displacement from the y-axis at a given time. So at 3 seconds, where were we? We were at 30 meters. 30 meters what? Or I'll say it this way, 30 meters north.
You can put like just 30 meters in the negative ones, you put like minus in the number.
Sorry?
Like we can put just 30 meters, and in the, for example, letter D we put minus 20 meters. We don't put the north one. Yeah.
You would have to be explicit what you mean here. Like you'd have to say it this way, positive 30 meters.
Okay.
You'd have to explicitly put that plus sign in there, just so I know you know what you're talking about. 5 seconds, we are still at 30 meters, so positive 30 meters or 30 meters north. 8 seconds, where are we? We already said this one. We were at 0 meters, back where we started. So it's relatively straightforward. I'm hoping you guys are comfortable reading things off the graph. Comments, questions, concerns? Okay, then flip the page. You've done this already, but you know now that the average velocity can be found off of these things by calculating the slope of a line segment, or we can use V average equals displacement over time, depending on the time interval that we're given. So this guy here, 0 to 3. You stay on this slide. I'm going to flip back and forth. 0 to 3 we've already done. We found it using slope, and we found that the velocity was 10 meters per second. Here we found using slope, and it was, what did I say? It was 10 meters per second. 3 to 6 seconds was that section B. We also found using slope. 0 meters per second. 6 to 9 seconds we found using slope. We found that was negative 15 meters per second. And 0 to 6 seconds. You stay on this page, I'll flip back here. If I wanted the average velocity from 0 to 6 seconds, could I calculate that using slope? Is there a line from 0 to 6 seconds? You could make one. But as far as the position time graph or the displacement time graph we're given, that line doesn't already exist. So if we found this thing using slope, making our own line in here, what's the rise, what's the run? Rise is 30 meters, the run is 6 seconds. So then our slope here is 5 meters per second. Alternatively, I'll flip back. We could use average velocity equals, average velocity equals displacement over time. That thing was displaced to 30 meters. It took 6 seconds. It's equivalent, should be equivalent. It's this, we're using the same set of data. But the implication here is this, that it doesn't matter. So when we're asked about like, what average velocity actually means, It doesn't matter if you ran to your 30 meters and then sat there for 6 seconds, or if you just continue to slowly plod your way along for 6 seconds. You're going to end up at the same point at the same time. This is the analogy of the tortoise and the hare, right? So if you wanted to add that line in here and calculate slope, you'd be welcome to do that too. Or you can just read the points off the graph for something like this. It's equivalent at this point. Flip the page. Here we go. Keep going. Sorry?
Can you go back to the page? The last one. No, the second page. The last one. Thank you.
Okay. The one that we haven't done yet is this idea of instantaneous velocity. Thank you. Here we go. Instantaneous velocity. What is instantaneous velocity? No. Acceleration we're going to talk about. Yeah, sure. Connor, keep going. What is instantaneous velocity?
You have speed immediately, or you have speed that takes 0 time, I guess. I don't think that's possible, though.
So let's redefine. Let's go back and look at average velocity. Okay, so average velocity was what? Okay, so your totals. So another way to think about average velocity is to think about it as, so if it's your total distance over your total time, this is the velocity over a length of time. You're on a road trip and you're going for 6 hours and you cover this distance. Your average velocity, you might not go exactly 100 kilometers the entire trip, but, or sorry, 100 kilometers per hour the entire trip. But if you were going 120 sometimes and 80 some other times and 60 some other times and maybe you did 140 because you're crazy, all of those different velocities could average out to a 600 kilometer road trip in 6 hours, giving you an average velocity of 100 kilometers per hour. So your average velocity is a velocity over a length of time. Your instantaneous velocity is your velocity right now. And in the questions I've given you, the average velocity, I mean, when we think about it in some of those questions, it was a constant, sound was traveling at 340 meters per second the entire time. It was things that don't speed up or slow down. But now we're going to start dealing with things that are able to speed up and slow down. And so to be able to figure out what their velocity is right now as they're accelerating is going to be something that's going to be useful for us to do. How we do that on a graph like this is we take the slope of a tangent line. Let me explain what's going on here. We have a curved graph right here. This is going to be, it's not listed in here because the photocopier cut it off, but this is position, this is time. So what does a curved line like this tell you on a position time graph? Yeah, Connor.
That whatever's moving isn't moving at the same rate that space is moving.
Okay, so the rate of change in position i.e. the rate of change of position is what? No, but what is it? But what is it? What is rate of change of position? How quickly your position is changing is your... No. Rate of change of position is velocity, how quickly your position is changing, that's velocity. The rate of change in position, i.e. your velocity, is itself changing. That's what a curved line represents on a position time graph. Now, if your rate of change of position, or if your velocity is changing, what can you tell me about what the object is doing? Sorry? It's moving. Tell me more. Its speed is doing what? It's going up. So it's speeding up. In this case, speeding up. We haven't talked about it yet. But speeding up means you are what? Big A-letter word.
Slowing down time.
No, you are not slowing down time.
I mean,
You're accelerating. Thank you. I mean, technically you are slowing down time, but you haven't learned about how to do that yet. We'll talk about that later. Okay? So when we have a curved line like this, we can't find the slope of a curved line because the slope is constantly changing. So what we do is this. We draw a tangent line. Now a tangent line is a line like this. So this guy here is a tangent line. Does anyone know what a tangent is? Hands up if you've heard that word before somewhere other than trigonometry. Okay. It used to be part of the math curriculum. It is no longer. A tangent line is a line that hits a curve in exactly one spot. So this particular tangent line hits the graph right there. This line here is not a tangent because it punches through the graph there and there. So we've got a tangent right there. The beauty of the tangent line is the tangent line actually gives us a slope we can calculate. If I take that point right there, and I draw my tangent line, now all of a sudden, I'm able to find rise and run at exactly that point right there. Manuel, wake up. What this is going to give me is my velocity at, I'm going to call this, I'll go down, draw a vertical line here, I'll call that time t. So by drawing a tangent line, I'm able to find the velocity at a specific point in time, which is not something that we've done up to this point. This right here, I know the bell's about to go, just you're getting restless, that's okay, is the beauty of calculus, which I'm not going to introduce you to, but this is the beginnings of ideas that you're going to learn about when you take calculus. Yes, Connor?
Right, so calculating the whole line.
So we're taking, at that point, by drawing a tangent, and we extrapolate that data into a bigger line, we find the slope of that entire line, yeah.
Would there be like, I don't know, circle you could say you have an infinite amount of different lines added together?
Theoretically, yeah.
But, so technically you would just draw a ton of lines.
If I asked you to, yeah. Okay, you guys can pack up. Have a great day. When the bell goes, you may also go. We'll finish this tomorrow. If I'm confusing you as we go, please do ask questions. You're gonna have to be able to do this. We're gonna do a lab in a couple days that requires you to do this. So please do ask questions. Don't let Connor be the one to monopolize all the conversation.
That's not a good idea. I don't really know what I'm talking about.
Okay. Bella's supposed to go. You guys can go to third block, or if you're on first floor, it's lunchtime. Have a good day. See you later.
Have a good day. It's party time. What do you want?
First floor, everybody's gonna go to their beach off class. Second and third floor for Tracy class, you got 4 minutes.
Well, have a good day, see you later.
See you later.
Will be getting their lunch. The second and third floor classes head to class. First floor, you are on lunch.
See you later.
What is the class now? The block?
C. B.
Alright, see you, Mr. Rivera.
See you later, Connor.
Yeah.
Yep.
Can I borrow my leadership computer again today?
Sure.
Thank
Do you
you.
have your own laptop?
No, I haven't had one yet.
You've never had your own laptop.
No, I did, but my English teacher accidentally broke it, and I still haven't gotten one yet. We're going on Monday, and I have an iPad, but I keep forgetting it.
Gotcha. Like,
Yeah.
oh, it's like she destroyed it.
Well, it's not broken, but it's not working. It's not repairable.
How do you know? What? Oh, because it fell off your desk. What's actually broken on it?
The hard drive.
Well, you know that? Like you took it in and they're like, yeah, the hard drive's dead?
And there's like the blue screen of death, and the fan is making a lot
Oh,
of noise.
fun. So it might not be the hard drive, but it's blue screened. Okay, cool.
Yeah.
Good luck with that. Okay. Emma, can I talk to you? Oh, dang it. Why